Welcome to the next video in a course in discrete math. This is lesson 6. We'll be talking about the precedence of the operators and a brief word about bits and bit strings. So what you can expect to find in this video is going to be a definition of the operator precedence rules, and then definitions of bits and bit strings and the bit string operations. We'll see examples and exercises. So as we proceed to discuss increasingly complicated propositions like this one, the glut of parentheses is a little bit hard to read. It's just not so nice to look at that. And we have a strategy for cutting down on the clutter. And it's a strategy that's basically familiar to sort of secondary school mathematics or wherever you would encounter this. I don't know, elementary, middle school. Anyway, so you could write this mathematical expression 1 plus 2 times 3 in that way, but you don't have to. You could just drop the parentheses, and that's because we tend to sort of all around the world assume that multiplication comes before addition. So to compute this, we all share this rule that you would not compute the plus first, but instead you would compute the multiplication first. Now, that doesn't mean that you couldn't express the plus first if you wanted to. It's just that that expression would require the parentheses to indicate that those come first. And so both expressions can be expressed with or both computations, I guess, could be expressed with our rules. Just one of them requires parentheses and the other doesn't. This rule about what comes first, at least in the United States, is called PEMDAS. So that's like parentheses, exponents, so on. I know in other parts of the world, they, instead of calling them parentheses, they're called brackets. And instead of calling it exponentiation, then it's called, I think, like order or something like this. So I think like maybe in the UK, it's called BODMAS or something like that. But in any case, we all have some rules, and they generally, with only slight exceptions, we all kind of agree that like parentheses are or brackets are the strongest indicator of order. It always comes first. Usually exponents come next, and then either multiplication or division. That can sometimes differ between countries. But anyway, so the point is that we have this system of precedence rules for the mathematical operators, and so we're basically just going to reproduce exactly the same idea for the logical operators. So in the same way that we do parentheses first, well, when it comes to our logical symbols, parentheses will, of course, still come first. It's going to be our way of indicating when the standard rules of precedence need to kind of get overridden. So parentheses come first, as always, but if parentheses aren't around, like in an expression like this one, then the order of operations to take them in is given by this sequence. So negation comes first. And so since negation comes first, if we're going to read this proposition, it would be the same as if I put parentheses around the negation P, because if negation comes first, then this negation P is sort of the negation is binding immediately to the nearest proposition, which in this case would be P, as contrasted with what, it would be possible to read it as the negation being applied to everything. But no, because our rule says that negation has the highest binding precedence, then this expresses how to read that negation, right? What order that comes in. Okay, next, the conjunction is the next higher precedence operation. And so we would take the proposition to its left and the proposition to its right. That would be negation P, and on the right it would be Q, and those would be joined together by the conjunction rather than any other reading where a different reading is possible. But we proceed likewise so on. So disjunction comes next, so we would put parentheses around that. Next comes the O plus. I think the textbook actually leaves out O plus, and so I'm just choosing of my own accord to place that in a in a place that I would find a sensible placement for the precedence rule. But there's no right answer anyway. So it won't really matter because I don't think we'll ever deal with O plus without using parentheses to indicate and be totally explicit about what order we intend. But anyway, so after that, then conditional comes next, and that's the only symbol left, so we're basically done. So anyway, that was a quick little demonstration or a walkthrough that these two expressions, right, if I were to not have any parentheses, then these two would be read the same way, right? Because of our precedence rules, you would know that the negation comes first, and so you would need these parentheses to tell you that, and so on. Now, just to briefly discuss bits. The idea of a bit is it's a digit that is either 0 or 1. We think about and talk about bits a lot in computer science because computers store zeros and ones, and so we want to do a whole bunch of calculations and reason about these kinds of things. Now, it may be worth knowing, why do we form bit strings, right? A bit string is basically just going to be a sequence of bits. So that's a bit string, there's a bit string, there's a bit string. Bit strings are just sequences of bits, and in particular, we're going to focus for the rest of this video on a byte. A byte is a sequence of 8 bit strings. Typically, a lot of data types that are in a computer are stored as bytes, as 8 bits. So anyway, we're just because that's so useful in computer science, we're just going to focus on that. You can have a bit string of any length, but I figured we might as well just focus on bytes for the purpose of this video. And just to sort of underscore the use and importance of a byte, well, okay, if we have bits, we have 0 and 1. Well, you might think, okay, that's enough for us to represent the number 0 and the number 1. But how would you represent the number 2 or anything bigger? Well, you're going to do it with a byte, right? Typically. Not always, but typically. And so, in fact, just for sort of consistency's sake, actually, to represent the number 0, we wouldn't actually just use a single bit. We would actually use a whole byte made up of all zeros. So that's how a computer will often represent the number 0, as a sequence of 8 zeros. And if we wanted to represent the number 1, it would be very similar. If we wanted to represent the number 2, that's where things get a bit interesting. Well, it's a lot like how if we took the numbers 0, 1, 2, and so on up to 9, well, we've got a special designated symbol for each of those numbers from 0 up to 9. But what happens when we need one more and we've run out of symbols? Well, we reset that symbol back down to 0, but we add an extra, increment the next digit to one bigger. And then from there, we can kind of do it all over again, right? We now just take that 0, increment it up to 1. If we want the next one, we increment the 1 to a 2, and so on. But again, when we run through all of our symbols from 0 up to 9, and we need a next number, we increment the number to the left, and we set the units digit back down to 0. So anyway, that's just for analogy to how we standardly do things with numbers. If you're working with bits and bit strings, well, you run out of digits just as soon as you have a 1 here. So if you want to represent the number 2, then you reset that bit back down to 0, and you increment the next bit. it reminds me of this joke that computer scientists love to tell, which is that there are 1-0 kinds of people in the world, those who understand binary and those who don't. The joke is that 1-0 is how most people read 10, but in binary, right, when your base is 2, just to say basically that when all your digits are bits. Then this is how you represent the number 2. So this is really saying to a computer scientist that there are 2 kinds of people in the world, so on. So on this slide, it's explaining much of what I've already talked about on the previous slide. I'll just go ahead and mention, which actually might be already on the next slide, I can't remember. But if we wanted to represent the number 3, then we would, again, right, we would just increment that units digit, which would be right here, right? So from where we are at 2, we would simply take that 0 and increment it up to 1. But it'll be interesting, what do we do next when we want 4? Well, we're gonna reset the 1 to a 0, but then we're gonna come over here and we're gonna increment this bit. But this bit, already, right, when we do that, it runs out of symbols because there's only 2, and so if we increment 1, we need a new symbol, but we, can't have one, basically. So what we do is we reset it and increment the next bit, very much like we do in our standard number system. We're just restricted to bits rather than digits from 0 to 9. And then everything else just stays the same. But so this is the number 3, this is the number 4. And so on, right? And the pattern continues, and you are encouraged, if you're new to this, to, keep generating the numbers until you feel like you've got the hang of it. But here I'll just demonstrate the numbers up to 6. So here we already saw that this is 4, and then 5, we would just increment that last bit one more time. Then when we increment it, it turns into a 0, but we increment the next bit, and so on. Now, why have we been talking about bits when the current subject seems like it's supposed to be about logic? Well, for a number of reasons that we can't quickly talk about, so I'll just have to promise you that there are reasons why, when dealing with bit strings, we would like to compute some of the logical operations. So if you think about how, we've kind of got these values false and true in logic, and we can compute, these operations. So our rule for false conjunction true is that it evaluates to false. Well, if you have values false and true, we could kind of treat them as if they were the values 0 and 1. And we could basically make a similar rule. If we identify 0 with the value false, not for any intrinsic reason necessarily, but just it's a convenient identification to align 0 with 0 with false and 1 with true. Then the corresponding conjunction rule for bits would be that 0 playing the role of false and 1 playing the role of true would evaluate to 0 because that plays the role of false. And again, the reason why we do this is for computer science reasons that would take a little too long to explain. So just trust me, like for those interested in computer science, I promise this will be useful later. For those not, well, then this may just be an interesting little application. But in any case, we've seen this example with conjunction. We could do likewise for the other operations. And so here, using our precedence rule that disjunction would come earlier than O+, then we would compute 1 disjunction 0, which would evaluate to 1. And then we would compute 1 O plus 1. That's the exclusive OR. So with a 1 and a 1, it evaluates to 0. And so there you have it. Right here is another example computation with bits and the logical operations. And finally, let's bring it all back around to bit strings. So if you have a bit string of all these bits, right, in particular a byte, we can perform the logical operations on these bytes, and it's just going to go the way you'd hope it would with the very simple rule that you do it bit by bit, right? So to take this expression and start computing, we'll start computing the, well, I guess we could just start computing the negation first. Let's start there. So if we want to negate this byte, then we would take 0 and exchange it for 1, right? Because just how the negation of false is true, that is what we're doing here, basically, but with a bit. And so that 0 turns into a 1, and that 0 turns into a 1, and that 1 turns into a 0, and so on throughout the rest of the byte. Likewise, over here, we can compute the disjunction of these two bytes. So 1 and 0 make 1, 1 and 0 make 1, and so on, until you get all the rest of this byte as the result of the calculation. Now, we can then, having computed that, we can compute the conjunction of these two bytes. We get this resulting byte, and there you have it. There's a demo of computing these logical operations on bytes. And so now we're going to have a few exercises. So one thing that's worth thinking about and appreciating is, does the order of operations really truly matter? And when I say that, what I mean is, is there ever a situation where if you read the operations in the wrong order, you would get the wrong answer? We know that happens very sort of transparently with 1 plus 2 times 3, because if you read it in the right order, you'd get 6 plus 1 is 7. But if you read it in the wrong order, then you'd get 3 times 3 is 6. So you'd get the wrong answer if you did the order of operations incorrectly. Is the same true for any propositions using those sort of logical operators? And the answer is, well, I guess you're going to find out. So go ahead and make the truth table for this proposition, and also make the truth table for this proposition. And then when you have them, argue whether or not the order of operations truly matters. And then kind of do likewise with this proposition and this proposition, right? So make the truth tables for each of those and compare them, and make a case for whether or not the order of operations matters there as well. But, okay, so I guess, it's I'm giving it away that, yes, the order of operations does matter. It's probably obvious, but sometimes it doesn't. And in particular, if your proposition is made of only conjunctions, then the order of operations turns out not to matter. So go ahead and make the truth tables for these two propositions and point out that when your proposition is made only of conjunction, then in fact the parentheses don't matter, because both ways of parenthesizing give you the same truth table. And likewise, the same is true for disjunction. And then it's a more challenging and interesting question. What about the conditional? If you parenthesize this in two different ways and get the two truth tables, will they be the same? And likewise for O+. So go ahead and draw those truth tables and decide for yourself. Now, in this exercise, you are to take a proposition like this and draw parentheses so that the meaning of this proposition, which is given by the precedence rules, right? So we know what this means because of the precedence rules, but write it with parentheses such that if we took the precedence rules away, it would still mean the same thing. So just to give you a demonstration of what I mean, because that can sound a little bit confusing, imagine that we had this proposition. Well, if I wanted to parenthesize it so that it has the same meaning, then I would put parentheses around the negation P so that you couldn't possibly read it that way. And so, with the parentheses being added like this, if we took away the parenthesization rules, then we would know exactly what this means, and it would have the same meaning as that. And for the last couple exercises, show that if you take any byte, right? So X here is just a single letter, but it's really just a variable for a byte. So it really is standing in for 8 unknown bits. But show that no matter what X is, right? No matter what byte X is, if you O plus it with all zeros, you just get X back again. Similarly, and perhaps even easier, show that if you, inclusive OR it with the bit string of all ones, that you just always get the bit string of all ones. Okay, and then finally compute this operation on bytes. And I'd like to end the video with an invitation to ask questions. So if you found anything confusing in this video or in corresponding portions of the textbook, then please leave a question in the comments below. If I can address it in the comments, I will. Or if it is a more substantial task, then I may make a video and include it in the playlist.